Okay, so that's us all. Now, there's something else you need to know. Okay, and it's called standard enthalpy of formation. This is also kind of fun to do. Well, fun for me, maybe, hopefully fun for you. So we have something called standard enthalpy of formation. It's the enthalpy change required to produce 1 mole of a substance from its constituent elements, okay, or from its free elements. So the elements must be in their standard states, a gas, liquid, or solid, at STP, 298 Kelvin, 1 atmosphere. Now, I have your STP. What is the STP normally for gases? We talked about STP. It's, well, standard molar volume is 22.4 liters. But standard temperature is always usually 273.15 Kelvin. But when they talk about standard enthalpy of formations, the standard temperature becomes 298. And the reason why is because they assume your room temperature, and chemists are concerned with reactions that occur at room temperature. That's just what we normally deal with. We're normally not sitting in a room or outside at 0 degrees Celsius, normally, unless you're in Alaska or the Arctic or something. Okay, so 298 Kelvin has been used to replace the standard temperature for enthalpy calculation. So the standard heat of formation for a pure element is always 0. So the standard elements are the benchmarks with which to measure heat change. And there's this table here, and right now it looks like a whole table full of numbers that makes your head hurt, but it's actually not that bad. You won't need to memorize any of this, so don't worry. Okay, if I give this to you on the test, I'll either give you the values that you need from the table, or I'll put the table somewhere in the exam packet, but usually I just pluck the values out that you need to save you time. But just to point out some features of this table. Okay, so all of these units for the heat of formation are in kilojoules per mole. So again, it's the energy change that you need to produce 1 mole of that substance. So shouldn't be surprising then that the pure elements are always 0, because from the pure elements, well, if it's already a pure element, it's already formed. So you take liquid bromine. Okay, why is it 0? Well, Br2 is one of the 7 diatomic elements, right? Question, how come Br gas is not 0 versus Br2? Well, Br gas is not the standard form of the element. Okay, liquid bromine is the standard form of the element. If you look at bromine at room temperature, it's a diatomic element, and it's a liquid at room temperature. Take calcium metal, okay, under normal room temperature conditions, 1 atmosphere, it's a free element, it's pure element, 0, right? Take graphite, carbon, 0. Okay, diamond, not quite standard state, but it's close. Okay, but it's not quite standard state. Some other features, let's look at the other elements. CO2 gas, okay, that's also 0, that's a free element. How come it's gas? How come it's not liquid for the 0 here? Because at room temperature, chlorine is a gas, not a liquid. So notice how like bromine is a liquid versus chlorine's a gas. That just owes to the normal boiling points of the halogens. Okay. Fluorine gas again. Do they have iodine in here? I don't know. Let's see. Anyone see iodine? I don't see it here. But what do you think the enthalpy of formation would be for I2 solid? It would be 0, right? Why do I say I2 solid? Because at room temperature, iodine is a solid, right, in its pure form. Here we go with another free element, rhombic sulfur, right, S8. Okay, that's also 0. Sodium metal by itself, 0. Silver metal by itself, 0. O2 gas by itself, 0. Okay, so these are just the normal standard states of the elements. All of these other compounds are formed from their elements. So if I wanted to write a reaction for the formation of calcium oxide, solid, all right, it's negative 634.9. Okay, how would I write a formation reaction for that? Alright, so calcium oxide is solid. Alright, the enthalpy of formation is negative 634.9. Kilojoules. What are the standard elements that would produce that? Ca solid plus O2 gas. Right, so is that balanced? It's not, right? So how would I balance that? Now here's one of the weird things. They usually tell you to not use fractions when you're balancing, but for balancing for the sake of holding true to the definition of a formation reaction, you would have to leave this as 1/2 oxygen. Okay, and it's because the definition of a formation reaction is the enthalpy change associated with producing a coefficient of 1 mole of that substance. So I would not get rid of the fraction in this case. I would keep it as just a coefficient of 1 here in front of calcium oxide, and I would have to leave this as a 1/2 in front of the O2 to maintain the coefficient of 1 here. Okay, so all formation reactions, by definition, the enthalpy change required to form 1 mole of that substance. All right, we'll do some more. All right. Okay. Let's do some other ones here. All right. So write the thermochemical equation for the formation of each of the following. So F2 gas. So I want to form F2 gas. Can I write a formation reaction for this? Or is F2 gas already in its standard state? Yeah, F2 gas is already in standard state. So to go from F2 gas to F2 gas requires no energy, right? So it's 0, right? 0 kilojoules. What about Br2? All right, Br2 liquid to Br2 liquid.
It's also 0.
That's also 0. So again, if it's already in standard state, there's no energy change. What if I wanted to do C2H6? Oh, C2H6 gas. Excuse me. What is the enthalpy change for that? So if you look up C2H6, you can find it here. So you can say, okay, C2H6 gas, that's negative 84.68. So you would write here, negative 84.68. How can I complete this reaction?
In our package, just it's not negative. It's a positive on our table. Yeah, it should be.
This shows positive here?
Right.
Yeah.
There's no negative sign.
How is that? It's just a copy picture. I don't know.
I think it's because it's so small.
Maybe it's because it's so small. Okay, but believe me when I tell you, I'm not going to give this exact thing to you that small on a test. Okay. Maybe because it's just fitted on a slide and it's, you know, put in outline form. Anyway, so it's negative. Take my word for it. Okay. How would I finish this reaction? What do I have in terms of elements here? I've got carbon and hydrogen. What's my standard form of the element for carbon? We can look at this table. Carbon, graphite, right? So we could say, okay, we got C solid, and then for hydrogen, what's my standard form? I have H2 gas, right? Alright, and then I have to balance it. So I need to put a 2 here and a 3 there. So that's how you flip. And then it's balanced. Do I have to do anything with this number? No, I don't. Okay, it's just, this is the energy change to form 1 mole of the substance. All right, here's the last one's harder still. Okay, so H2SO4 liquid. Okay, so I want to form H2SO4 liquid. So I look up H2SO4 liquid here, and I have right here. So this negative there. That's a negative 2. It doesn't show on yours. There's a negative there. That's negative 814.0. What are my standard elements? Well, what elements do I have in the formula? H2SO4. I've got H2 gas, right? For sulfur, what's my standard form of sulfur? Again, I can look at the table here. Rhombic sulfur, S8. And the last element, O2 gas, right? So S8 would be solid, rhombic, okay. And then we'd have to balance it. Hydrogen's already balanced, but we do have 1 sulfur here, well, we have 8 sulfurs here.
How would you know which sulfur to use?
So from the table, the one that has 0 for its standard state. So when I'm looking for elements that produce that substance, the things that I write on the left side of the arrow are going to be the ones that have 0 for their number, because that tells me that's the standard state of that substance. So I know to use S8, solid rhombic. I know to use that because that one has 0. I know to use H2 gas because that one has 0. I know to use O2 gas because that one also has 0. Okay. How do we balance this? How do we balance it while keeping this coefficient 1 is the question. Yeah, so if I only want 1 sulfur here, I got to put 1 sulfur there. It's weird, but it maintains our coefficient of 1, right, for the sulfuric acid. What about for the oxygen? Yeah, I got to put a 2 in front there. Now, if I balanced this differently, like let's just say instead of having 1/8 here, I had 8 in front of the product, to get 8 sulfurs. What if I did that? Okay, at that point, I'd have to multiply this delta H by 8, right? So, one more? Do you want to do one more? Somebody pick me one on the list. Let's have some fun with this. Like, pick the hardest one you can possibly think of.
Pick one. NaHCO3.
Are you sure it's hard enough? All right, let me see.
So you didn't pick
And you had
Sucrose.
oh, that's here? You picked this one. All right, let's do that. Oh, it's got 4 elements. Oh, we can't do that one. It's too hard. No, I'm just kidding. Let's do that one. That's fine. If you haven't noticed, I like that phone. All right, so we'll do sodium. Okay, continuing on with always practicing our nomenclature, what's the name of this? Sodium bicarbonate. It's what I used to put out the acid spill that Austin, he's not here. Okay. Anyway, we put out Austin's oil spill last time with sodium bicarbonate. So if we're going to form one mole of sodium bicarbonate, delta H equals negative 950.8 kilojoules. All right, so what are the standard forms of those elements? All right, Na solid plus H2 gas plus right, carbon solid plus O2 gas. All right, and then we balance it. One sodium on both sides, we're good there. Two hydrogens, but only one hydrogen on the product side, so what do we do with the hydrogen? We make it 1/2. All right, and then for carbon, we got one on each side. For oxygen, there's 3 there, but there's only 2 here. What do we do with that? What number times 2 gives me 3? 3 halves. So this will be 3 halves. So 3 halves times 2 oxygens gives me 3 O atoms, which balances to 3 here. And that would be a formation reaction to form 1 mole of sodium bicarbonate from its pure elements. Right? Definition of a formation reaction. So this will come in handy when we get to chapter 9 or 10 and we do lattice energy calculations and stuff like that. Okay. How do you feel about formation reactions? Do you get the concept? All right, enthalpy, heat required or consumed or produced when you form 1 mole of that substance from its standard elements. Okay, and how do you know which ones are standard? Whichever ones give you 0 on the table. That's how you can tell. All right. So from these heats of formation, we can also calculate the enthalpy change for an unknown reaction. So what if you're not given a series of reactions like what we did with Hess's law? What if you're not given that? We actually have an equation to help you calculate it regardless of whether or not you actually have the formation reactions. And this is the reaction you'll use. So the enthalpy of reaction is equal to the sum of the heats of formation for the products with their molar times their molar coefficients minus the sum of all the heats of formation of the reactants times their molar coefficients. Okay. Again, this is a nice plug and chug problem. So here's a question. Calculate the enthalpy change for the combustion of C2H2 gas directly from heats of formation. See table in the textbook. In other words, see the table in the notes. When you see it done this way, you're going to be like, gosh, why do we have to go through Hess's law then? But sometimes you're not given the heats of formation for everything. Okay. Okay, so we still have our reaction. It's asking us the same question as what we had with our last Hess's law problem. What is what is this value? Okay, but now we're going to just take it from the table of the heats of formation. So we have sum of our heats of formation for the products minus the sum of heats of formation of our reactants. So for the products, which ones are the products? CO2 and water are the products, right? So we're going to say, okay, 4 times the value for CO2 plus two times that for water minus 2 times the C2H2 heat of formation plus 5 times the oxygen heat of formation. So we're going to look up the values for delta H from the table for these compounds. Okay, so we have 4 times negative 393.5 kilojoules plus 2 times negative 241.8 kilojoules minus 2 times the heat of formation for C2H2, which from the table is 227.4, positive 227.4. And 5 times for that of oxygen, which is always 0. All right, and then from that, what do you get? What I suggest you do is just calculate 1/2 at a time. So on this side, you should get 2,057.6, okay, minus this 2 times 227.4. All right, this is a negative number here. So negative 2,057.6 plus a negative 454.8. Alright, and you're getting, should get 2,512. .4. Negative 2,512.4. So is this the same answer as what you got in the Hess's Law problem we just did? Yes.
Yeah.
So provided you have all the heats of formation, Hess's Law, we used Hess's Law to figure out what this was. And you might ask, well, why would we not use this, and when would we use Hess's Law, right? Isn't that a question that maybe comes to mind? Well, we did a problem using Hess's law with formation reactions, but I can tell you right now, there are other times when you want to find delta H of a reaction, and not all of the reaction steps are formation reactions, right? So it's a lot more difficult to do Hess's law, if you don't have the formation reactions. Or it might be that the reactions that you have to use in Hess's law, not all of them are formation reactions, but you can derive the thermodynamic data from other processes. So maybe a reaction has been done in calorimetry, you know the delta H is from that, but you don't necessarily have the heat of formation for it, right? So it's not always doing heats of formation with Hess's law, you sometimes use other steps that are not formation reactions. Okay, so negative 2512.4 kilojoules. All right.
Did you mean to put subtraction between those two values?
Well, it's this negative number plus this negative number here.
It is minus.
So you're kind of adding two negatives together, basically, right? Let's do it this way if you want. We can just say minus that plus value. Okay. So this half gives me negative 2057.6. This half gives me positive 454.8, but there's this subtraction sign here. Okay. Questions regarding using standard heats of formation to figure out what the enthalpy of reaction is. Why do we care about enthalpy in general? Like, why do we care about it? Do we care about how much energy we can get out of chemical processes? Do we care about how much energy we can get? Because it's kind of one of the defining issues of our day, right? We care about how much energy can we get out of the process because we're using that to do work, right? So thermodynamic data is always important for that reason. Okay.